So I would like to thank the organizers for giving me this opportunity to come back to KITP, the Santa Barbara, very, very beautiful weather and very exciting place. And so I didn't realize that this session is solely actually devoted for thermal transport until today. So, I'm going to talk about this electrical transport. But I hope that this is going to be interesting to you. And I'm focused on the chiral antiferromagnet and the electrical and strain manipulation of these systems. And before going to the details, I just want to thank the work, make the work possible. And this is the group of my members and at UTokyo and ISSP, and also RIKEN, MPI Dresden, and also these GHU colleagues and Cornell University. So the context I'm going to talk, so it's about the topological correlated phases, and there are numbers of ways of finding these phases. But one way of doing so is to blend or combine this atomic or cluster multiple onto these various type of exotic, exciting topological band structures, and chiral spin liquid or magnetic topological semimetals or quantum anomalous Hall systems can be actually realized, and we have already observed. Noticed them, and and it could actually have various functionalities, and eventually could lead to applications. And for this context, we're going to focus on the magnetic biosemimetals, and in particular, this manganese 3X systems. And we show some evidence for this semi-metallic state, and we're going to focus on how we could manipulate them, their new functionalities. For example, a piezo-magnetic effect actually can be used to control the semi-metallic state through strain, or spin of torque by electrical means. And finally, if time permits, I'm going to talk about use these manganese 3X as electrodes, and try to see whether you can actually have tunneling magnetoconductance. Okay, so one of the is important functionalities, if you like, is the response beyond the magnetization scaling of these class of materials. So this you can see that this is a scaling law of the anomalous Hall or anomalous Nernst effect as a function of magnetization, and but these magnetic biosemimetal or magnetic magnets actually has the 2 or 3 orders magnitude larger enhanced response in comparison with the response you would expect based on the magnetization. And then actually you can sense the magnetic state using those the anomalous Hall and Nernst effect to build up a new devices such as non-volatile memory or thermal conversion, and also it also tells us that the large response can be obtained even though you don't have any magnetization. Okay, and such state, one of the prototypical system is manganese 3X. This is a material I'm going to talk about. We found a very large response as if it were a ferromagnet, despite the fact it doesn't carry the magnetization. And the 2 ingredient is very important for this system. The octopole, this is actually cluster type of octopole in real space, and the other one is a wild point in the momentum space. And this was actually, we didn't expect, and we actually experimentally discovered, and it was actually possible for us to electrically manipulate this biosymmetric state, actually first among other symmetric systems, and that was made in antiferromagnetic system, and it actually turned out it's so simple for us to manipulate this just using existing spintronics the technology developed for ferromagnets. So, for example, you just use the whole bar to manipulate the electric state, magnetic texture of this the biosymmetric state in comparison with other many this more complicated structure for developed for collinear or maybe recent the exciting alter magnets. Okay, so just I would like to go through just a few evidence of this biosymmetric state, and among many other evidence that existing in literature. And so this is a material that carries Kagome lattice. So and this Kagome metal, and it's a kind of a rare example of this antiferromagnetic Kagome metal. And that because of the geometrical frustration, it actually has 120-degree order. And if you take a look at it's not simple 120-degree order, it's that anti-chiral vector chirality is negative and leading to very tiny magnetization of the order of milli-μb that cannot be seen in this normal ferromagnetic domain, this unit of magnetization in μb. And instead, the whole resistivity is very large, comparable to the one in ferromagnet. And this can, and if we do the outburst measurement, we actually found the wild point nearby this hexagonal Brillouin zone, the K point, and this not only just wild point, but also the band itself, which actually produces wild point, turned out to be strongly renormalized. So there is a strong correlation effect due to the manganese 3D electrons. Another important point, this is actually a thermal, important thermal, the transport, the only slide for this, that this thermal transport analog of the Hall effect is a Nernst effect. And this is again another magnetization scaling. And for manganese retained, because of this 120-degree order, this is only tiny magnetization of this millitesla. So you wouldn't expect any Nernst effect, but it actually turned out provides a very large one, nearly the maximum size known for the ferromagnet. This actually tells you that there is a large very curvature nearby the Fermi energy, because this actually it's automatically telling that thermal conductivity is so large. So this means there has to be a source and drain of your very curvature, which is wild point near the Fermi energy. Another interesting point that despite the fact that it only carries such a milli-μb moment, one can actually control the magnetization so easily that as the 100 Gauss. So magnetization somehow pick up small field and then a whole resistivity flips. This tells us, so if we calculate the external field necessary to actually induce this size of whole resistivity, say several micromole centimeter, using orbital, ordinary Hall effect, it requires a few hundred Tesla. So almost like 100 Gauss can be is enough to control the few hundred Tesla impact on the system. So then, okay, so this is emergent electromagnetism. In order to actually find further evidence, further phenomena, new functionality, it would be more interesting if we can find other methods than just magnetic field, such as strain or electrical means. So that's what we did, and then we're going to go through some recent work on the strain. So let me just go through some the notion of the cluster magnetic pole. So if you do this multiple classification, of course the collinear phase is the most popular one, which is the simple dipolar one. But it turns out this cluster, this anti-chiral 120-degree order on this particular Kagome lattice turned out to share the same time Russell symmetry, the magnetic space group. And of course, this doesn't carry magnetization, so rank 1 is not available. So, and there's symmetry, spatial symmetry, inversion symmetry. So rank 2 is not available. So the final, the minimum rank available is an octapole. And you can actually see this magnetic texture as a Q equals 0, or a ferric order of magnetic octopole. So this is so simple that this breaks the time reversal symmetry macroscopically. And that's the reason why you see anomalous Hall effect. So if you like, you can actually take this octopole polarization as an order parameter of this observed anomalous Hall effect, and maybe it can be a linear relationship. Okay, and this is a kind of working principle, working hypothesis. Okay, then let's go to the strain control. So here comes the piezomagnetic effect. So for certain type of antiferromagnet, so the strain breaks the symmetry, and between magnetic sublattices induce the net magnetization linear in the applied strain. I describe it in this form. And this is lambda, this tensor, only available when you have this material break a time reversal symmetry, or preserve time reversal only in the combination with rotation and the reflection. So this has been, has a long history of the research. So, for example, the cobalt fluoride, manganese fluoride, 1950s. Moiré and Jaroszewski pointed out that this is a tetrahedral structure and actually has strain along 110 direction, can break a symmetry of the sublattice moment and induce a ferrimagnetic state. So the magnetization can point either up and down depending on the sign of the strain. So a tensile or compressive, you can change the magnetization direction. So under a magnetic field, of course, you can actually stabilize one of those magnetic state, and then in the presence of piezomagnetic effect, the static stress can mediate 180-degree antiferromagnetic domain reversal. So this has been already done like 1980s. So strain control of antiferromagnetic insulator has been already made, but there has been no such a case in metallic or wireless metallic states. So let's see how this works for the wireless metals. Manganese routine. So this material, of course, exhibits anomalous Hall effect, time reversal symmetry is broken, and should be available. And there is a linear coefficient, which actually has become simplified because of this the magnetic point group symmetry. And for example, if you take this in-plane magnetization, it should be linear with the sigma x, sigma y, sigma x, y. Okay. So if you actually apply in-plane strain in the material, so let's say Kagome plane, if you squeeze it, magnetization should appear. Let's see. And this is what our excellent former PhD student Equlas has made. He made a very high quality single crystalline sample, bulk single crystalline sample, applied a universal pressure along in-plane, Kagome plane. Along, say, this x direction or y direction, we found there is almost a similar phenomenon. So what's going on here is for the following. So if you actually increase this uniaxial pressure, so then systematically this magnetization going up, okay? And the field dependence stays nearly the same. So there's a two component of the magnetization. So spontaneous part and also field-induced part. And this spontaneous part is actually enhanced in plane stress. And the field-induced part somehow independent. And susceptibility is nearly constant. And if we summarize this, it looks like this. So magnetization spontaneous part is linearly increasing as a function of stress. Susceptibility remains the same. And this is exactly what you expect for the piezomagnetism. And this linear coefficient as a function of uniaxial stress tends to be quite large. And this is somehow something very close to the maximum life size known for the antiferromagnetic insulators. Okay, so what is the mechanism behind this? And Oleg and Sayak, former student of the Oleg at JHU, has made a lot of extensive investigation on this mechanism and found the various things, and one of them is exchange restriction, and that's which has turned out to be quite important. And so, of course, exchange restriction is the super exchange dependent on the distance. This is so simple. And when this antiferromagnet is frustrated, like 120 order. So if you bring these manganese, for example, closer to each other, antiferromagnetic correlation develops, right? It becomes stronger. Vice versa. So if you have this 120 degrees order anti-chiral texture, magnetization is so tiny, it's almost vanishing. And if you actually provide tensile stress, it becomes like a ferromagnet, right? Okay, so it develops ferromagnetic coupling along this X direction. So because it was originally almost zero canceling, the magnetization itself is canceling each other. So just tiny, tiny tensile stress is enough to flip the magnetization direction. So, and having this, the main body of the octopolar state unchanged. This is a very important point. So octopolar state is unchanged, but magnetization can be, the tip of balance can be, tweaked by this small strain. This is the beauty of frustration. So under the magnetic field, you should be able to align magnetization, of course. So what you actually expect is that, the change of this octopolar state. In other words, you should be able to switch your spin direction 100 by 180 degree. And if this is the case, and if the anomalous Hall effect is dictated by octopolar direction, you should be able to see the sign change of anomalous Hall effect. So let's see whether this works. And collaborating with Cliff Hicks at that time in Dresden, he moved to England, and he developed this very nice the piezoelectric cell, which can allow us to go tensile and stress, compressive stress both sides continuously, and within the elastic limit, we actually did this measurement very continuously without having any problem, and so reproducibly. And you can see that this is a renormalized Hall effect. The plus sign go to the negative as a function of uniaxial strain. So this is exactly what you expect for the anomalous Hall effect dictated by the octopolar order, not by dipolar magnetization. So in other words, this strain actually could mediate the 180 degree this spin rotation or reversal. Okay, this is for the strain control. Let's move on to the electrical manipulation and this biosynthetic state. And for this, I think we need to actually start thinking about how the magnetization process, because it's actually related to dynamics. And there are numbers of literatures, and I just pick one of the literature I like, the recent one made by Oleg. And this is the 3 sublattice antiferromagnet field theory. So this is more actually accessible to experimentalists, poor experimentalists. And the point is that so what you actually need is a small counting of your this antiferromagnetism to let all the spin process. Although three sublattice system is complicated, whether you don't know whether actually your torque you provide work constructively, right? But the field theory tells us that indeed, if you actually just make a small counting, that will allow you to have a precision. Around this small magnetized counted moment, and then this angular moment. This moment develops around this. So in his language, he found that this nx, ny, and z, this is vector chirality term, is the order parameter of these 3 sublattice, and they are precise around this angular moment. So the next question is, how can we actually develop small m? So that is the method for the spin orbital. Before going to that, we wanted to tell we have evidence of such a spin precession at the time scale of these terahertz. So because another important point is that omega is actually proportional to 1 over chi, or this exchange coupling. So the beauty of the antiferromagnetism is that in comparison to ferromagnetism, you can go faster dynamics to the terahertz scale. So the in fact this is TR time resolved magnetic optical Kerr effect. So the Kerr effect, which actually shows that the precession as a function of the delayed time, indicating this, spins or octopolar moment does precess at the time scale of picosecond. But it decays very rapidly, indicating there is a giant effective damping. And so this is actually useful for the switching for us to develop a memory, because once actually let the spins precess, it actually stops automatically. There is a strong damping due to, I think, I would say, strong correlation of this material. Okay, and so then how can we actually develop a small m? So this is the way to use spin orbit torque. The spin orbit torque is actually developed for this ferromagnetic spintronics, and this you need a heavy metal layer neighboring to the ferromagnetic material, which in this case perpendicularly oriented magnetization. And by sending current, you can generate a spin Hall effect, and the spin accumulation at the interface generate this M, and that's actually the spin torque to the spin Hall align the spin in the plane. And if you remove this current, this spin return back to the perpendicular direction according to the bias field direction. So it's called deterministic perpendicular magnetization switching by the spin orbit torque. So let's see whether this is going to be useful. And this is a kind of roadmap. This has been made for the spintronics, ferromagnetic spintronics field. And since the 20th century, this has been developing through this magnetic field control to the STT, spin transfer torque control. Now spin orbit torque control is a major research topic in the spintronics. And in particular, this perpendicular orientation turned out to be quite useful when you consider how to integrate these memory as dense as possible, because of it's consistent with the scaling of this magnetic bits. And so the question is whether, so this is also possible for the case of antiferromagnetic, memory, if you like to develop. So this is exactly what we actually made quite recently, and we found a perpendicular free switching. So full switching is very important for antiferromagnetic order. So this is experimental details. I should maybe cannot focus so much on this with the time constraint. But the point I would like to make here is that by using molecular beam epitaxy, we made this perpendicular magnetic switching layer perpendicular to this MGO. The Kagome layer is perpendicular to MGO. So how many minutes? Okay, nice. So there is, of course, the lattice mismatch between MGO and magnetic switching. So that actually provides a 0.2% tensile strain, which turned out to be later important for us to consider piezomagnetism. And the whole conductivity and the coercivity and etc. is quite very close to the bulk system. So very high quality thin film is available. And here comes the highlight of this work. So we send electrical current through this. So there's tungsten. This is heavy metal, and induce a spin Hall effect. And the spin accumulations actually send into this, and the spin current polarized along this perpendicular direction to the Kagome was actually introduced, and to see whether this actually flip. In terms of 180 degrees, so the octopolar direction, if you like, top to the up to the down. And if this works, you should be able to see the sign change of the Hall effect with the same amplitude in the case of the magnetic field control. And this is the one example of the field control of Hall effect using such a device. And using this completely the same device, we send the electric current large enough to switch the Hall effect. And then we actually did see the same magnitude of such switching, and and with very much smaller density of current than the ferromagnetic cases. And another important point is that we actually been able to demonstrate 100% L-class switching in terms of volume, and also the 180-degree reversal. Okay, so here comes some the mechanism. As I said, so strain is important for us to align the domain. So in this case, there is a tensile stress in the plane, meaning there is a compressive stress. This is Poisson ratio, and there is I mean the twofold. So that's actually stabilized twofold symmetry perpendicular to the direction this substrate, and spin current actually through the spin Hall effect applies spin torque constructively to each sublattice. So this is consistent with what we have discussed for the field theory argument. And another thing is that if we change the polarity of the current, one can actually go from this initial state to the final state, and finally coming back to the same original state, without going through any intermediate state. So that's actually different from the ferromagnetic state, this switching. So this is, I would say, some hypothetical statement at this point, and we hope we can actually see that this is proven by a time-resolved measurement. So this is kind of an interesting comparison for future development of such a memory. So the ferromagnets, and this is the now already adapted for this developing magnetic random access memory, which is now commercialized. And by using a topological antiferromagnet, we are able to make it 10 times smaller. And in comparison with Corinian antiferromagnet, it turns out we can actually make this device structure much simpler. So that is one the advantage of this topological antiferromagnetic materials. So how many minutes I should?
1 or 2.
1 or 2, okay. So final point I just wanted to actually tell you about is the quite interesting this tunneling effect. Maybe just let me go through. So of course this for MRAM we know that magnetic tunneling junction is a central part, and there's 2 electrodes, ferromagnetic electrodes, and sandwiching the insulating layer. Okay. So mostly MgO. And it's called the free and the reference layer. And because of this spin polarization, you could see fairly large MR. But anti-ferromagnet, obviously, there is no spin polarization. So that's the reason why no observation of such a kind has been made until now. But this material breaks time reversal. And in particular, octopole polarization form the polarization of the ferroenergy. So see whether it allows us to see a tunneling magnetic. So this is something we wanted to see, and this is a kind of research R&D roadmap, and the AG and the anisotropic magnetic resistance, GMR, TMR, and see whether this is possible for anti-ferromagnetic systems. And this is exactly what we recently find for octopole system. And this is, so I want to tell you a little bit about the detail. So this is, again, very important point is that MgO and the electrode magnetic splitting must have a very sharp interface in between. And by applying a voltage, we would like to see a tunneling magnetic resistance. In order to see that, you have to make an anti-parallel and parallel state of octopolar moment. And for this, we made actually use of MV and sputtering different methods. And we were able to make such a different state with having these electrons with a different coercivity. So this is a MOC, so magnetic optical Kerr effect. Looking down from the top, which actually shows the red curve. Looking up from the bottom, which is blue one. So there's, yes, I have one, two, three. I'm going to stop soon. Okay, so there's a finite region. Important thing is a finite region that allows us to see antiparallel octopolar state and this field range. And if there is any change in magnetic resistance, this is coming from the tunneling. And indeed, we see such a change, which, although it's not very large, it's only about 1%, but it's actually first time for the all antiferromagnetic tunneling junction. And we can actually make this even bigger by actually thickness of MgO thicker. I just wanted to make that this cannot be simply understood by spin polarization. Of course, as I said, there's bouncing small moment, magnetization, about 3 millirp, spin polarization of the order of 0.1%. So the simple-minded calculation tells you that about, the MR due to spin polarization should be 10 to the minus 6. So this, the observation 1% TMR cannot come from the spin polarization, but the octopolar polarization. And indeed, the theoretical, calculation has been made and found the 100% or maybe even larger MR is possible due to the large spin splitting due to this octopolar order, and this transmission along this perpendicular direction to this electrode is actually this coherent and can be momentum dependent, and that can lead to the magnetic resistance. So this is the end, let me summarize. So we actually find, so this topological magnet is useful, and in particular, so this magnetic 10, we found the piezomagnetism, and that allow us to actually change the sign of the anomalous Hall effect by strain, and also find the spin orbital switching allow us to actually change this magnetic or semi-metallic state, and we can use these state as an electrode to read their magnetic state through tunneling magnetic resistance. Thank you very much for your attention.
Thank you. Questions?
Thank you for the talk. Very impressive work. I have a question which you stress also here in the summary, the while aspect, the semi-metal aspect. So it's of course true that the while nodes carry Moiré curvature, but they're always nodes of opposite chirality, and then they cancel out. So experimentally, what is the precise evidence that the while nodes play a role in the physics that you observe?
Mm-hmm. Okay, thank you very much. So that's actually quite interesting. So first of all, we observed a very large anomalous Hall effect, which requires a large Moiré curvature, of course, and the Nernst effect also at the Fermi energy. You need to have a very large Moiré curvature, and there are a bunch of possibility. To produce a large Moiré curvature. Nodal line, nodal, plane, etc., and even gapped state can produce. And we actually go into the detail about the electric structure and this. Although diffusive, we actually see the signature of the power points at the outpace measurement, and also chiral anomaly, which I didn't show in this thing. Maybe, I didn't prepare that slide in this, but we did see a chiral anomaly, which is fully consistent with this the existence of wild fermions, and also the theoretical, the prediction for this planar hole, and also the magnetic resistance. Yeah.
So I agree that signature from the chiral anomaly, of course, or can be related to directly to the while nodes. But if you say there's a large barrier curvature, then this can arise from any number of places, and I would actually argue that two while nodes of opposite chirality carry in total zero barrier curvature. So in that sense, it's not so obvious that in the transport experiments that you did show that the while nodes play a role, or did I miss something in your logic?
I mean, if the while nodes actually actually form a ferroic type of arrangement like this, I think you should be able to see a very large response. And we actually did film energy, this tuning dependence of the Nernst effect, for example, and compare the result with theoretical the investigation. Of course, you need to actually take on account of U, which is a little bit we need to pay attention or take a care of. But this Nernst effect, for example, one can actually tune the size as a function of film energy and see whether it matches with the existence of the fiber nodes, and it does. Yeah.
Okay. So sorry to push this point, but that one could also calculate the barrier curvature, the electronic barrier curvature, from a band structure calculator or from some kind of model. Was this done, and does it agree with your data? So the calculation of the barrier curvature, of the electronic barrier curvature from a DFT calculation or from an electronic structure calculation.
Yes.
And that agrees with your data?
Yeah, and yes. As I said, so the barrier curvature as a function of film energy tells you exactly what you expect for this Nernst effect. And then one can actually change the film energy, the position by actually changing a little bit of manganese composition in this case. And because dominant this carrier, this film energy is 3D. And it turns out one can actually replace manganese tin, but a small amount of manganese. And then that actually goes to the film energy. That's we actually checked by photon emission spectroscopy. The film energy does shift as we see. Yeah.
More questions? So I have one very simple. So the coupling to strain that you described, so does it imply that magnetic excitation, this material would be hybridized with phonons, and is it something that phonons should contribute couple strongly?
That's right.
To magnet. So is it been studied? You see it in some consequences?
Yeah. So the ultrasound actually attenuation has been measured, and so this, yes, as you said, indeed there is a coupling between the phonon and magnetism, and the elastic modulus actually show strong anomaly at the T-nail. Yeah, and that's actually quite interesting. It's indeed magnetization or the spin texture is strongly coupled to this the mode, and they can actually identify which mode coupled to this elastic modulus, which shows a strong anomaly at the function the temperature, and it's actually consistent with this piezomagnetic effect. So piezomagnetic effect seems to show up also in this ultrasound measurement. Yeah, that's right. Yeah, and also shows a very strong field dependence because it carries a magnetization. Yeah.
Okay, yes. So it's very consistent.
Yes.
So I guess it's along the same line. There is I just want to distinguish. Is there a distinction between in the case of this tensile stress effect, there is a number of triangle lattice, for instance, materials which exhibit magnet-phonon coupling, and they are known to be multiferroics. Is there something special which allows you to switch the magnetization, or they all should exhibit that? I just didn't quite get that.
Okay, so here what is important is that these spins are really frustrated, you have, so in this particular material, it's a frustration, and that's tiny strain was enough to tip the balance between hit the balance of the cancellation of sublattice moment, right? So by just changing a small bit of strain, one can actually flip the magnetization direction, because you can actually change this, the counting direction a little bit. That was actually enough. And your question is that whether this can be applied to the other system. So yes, so if there is any symmetry that actually is broken for the so if there is a several different magnetic site, you might be able to actually induce a ferry state with a maybe different reason. In this case, ligands provide strong impact onto this magnetization direction, which actually different from one side to the other. And then you can actually, it was fully completely compensated, but the small amount of strain can actually give rise to the ferromagnetic state.
It sounds very general, because 180-degree structure is the one you're describing.
Yes. So, and if you actually use a magnetic field, you can stabilize one of those and apply strain, then you should be able to actually mediate this 180-degree spin reversal.
So in your geometry of switching using spin orbit torque, so when the magnetization switches in the Kavli plane, and then the octopolar order switches through out of the Kavli plane or inside the plane?
So you were saying that
so the antiferromagnetic part, does this rotate inside the Kavli plane or switch by going out of the Kavli plane?
Thank you very much. Yeah, that's a very important point. So in order to apply a torque, what is important here is that the spin polarized current has to go into this this magnetic routine with polarization direction perpendicular to the magnetic routine. This Kavli plane. So the spin actually somehow polarized along the perpendicular direction to the Kavli plane. But this is easy plane material, so it's almost and it's very, very tiny, and that actually provides a constructive torque. But and the octopolar moment switches within the plane, not coming out of the plane. Yes.
Thank you for the talk. My question is kind of selfish, because we did some research on the rare earth analogs of this structure, P63 MMC, and in those cases we never get this inverse DMI or this inverse antiferromagnetic 120-degree order. So I want to know, why is this inverse 120-degree order stable? And if it's Dzielodzinsky-Moiré interactions, why should they be strong in this type of structure?
That's very interesting. Yeah. So yeah, if you want to design a magnetic texture, we need to know that. Yes. This material has been known since 1970s, and there has been neutron diffraction measurement. And Nagamiya sensei, who is the theorist for antiferromagnetism, actually found a Dzielodzinsky-Moiré interaction along z-axis is very strong, and actually has a negative sign, which makes this spin to be antichiral. But the question is where does this sign comes from, right? Where does the sign come from? That part, I do not really have a very good answer for this. Maybe some of the audience, maybe Leon might have some. Do you have some answer to that? Why D has a special sign instead of providing? That part is quite interesting, but I don't really have.
But it's not the only material.
That's right. But you found the same. I see. Yeah, I don't know. So it's really dependent on the structure, but yeah.
All right. If there are no more questions, let's thank the speaker.